Right, this video is on the objective graph a limacon from a polar equation. And this is the second video on this objective. Hopefully you watched the first one. Right, that had a lot of stuff in it. So I'm just going to get right into it. So again, if you want to see more on the topic, click on more instruction at the bottom of the question and look at their videos, their notes, their examples. Hopefully those help you. Alright, so we're asked to graph on the polar grid r equals 5 times the sine of theta plus 8, right? So some constant plus some multiple of sine. This is an example of a limacon. Right, where the constant and the coefficient on sine are not the same. Right? Remember, when the constant and the coefficient on sine have the same absolute value, that's a cardioid. Right? A cardioid was a special kind of limacon. All right, so I'm going to go to my paper here, and we'll write this equation. It's 5 times the sine of theta plus 8, or 8 plus 5 sine theta. So that when we were talking about limacons, right, they were equations like this: a plus or minus b times the sine of theta or cosine theta. And remember, if the magnitude of a over b, I'll say absolute value of a over b. Remember, if this was less than 1, you had one of those limacons with an inner loop, or a 2-loop limacon. But here, it's 8 over 5, right? The constant term over the coefficient of sine is 8/5, which is definitely bigger than 1. So this is one of those dimpled limacons, or convex limacon. And this is between 1 and 2, actually, so it's more dimpled than it will be considered convex. But remember, this was it's like a circle, but part of it's kind of dimpled in. All right, it's going to look something like this, where there's a circle with a dimple. All right. So let's get into it. Now, you know me. You've seen my first video, and hopefully some other videos where I've been graphing polar equations by hand at first, making some rough sketches. I like to look at the XY version, where I just replace theta with x and r with y. All right, this isn't the rectangular version. It's just the way I would normally graph an old, graph trig functions back in the day. So y equals 5 times the sine of x plus 8. And then the way I would normally graph this kind of a function is the x-axis. Now remember, x represents theta here, and the y-axis, y represents r, right? Values of r. All right, and then this would have a period of 2 pi. Cut this into quarters. Plug these in, and the middle value is going to be at 8, the midline is going to be at 8, and the amplitude's 5, so the high value is going to be at 13, and the low value is going to be at 3. When I plug in 0, I'll get 8. All right, plug in pi over 2, I'll get 13. Pi, I'll get 8 again. 3 pi over 2, I'll get 3, and then 2 pi back to 8. And here's our sine wave. Okay. Now, if you don't know how to do this, go back to whatever chapter we learned how to graph trigonometric functions and refresh your memory. All right. So I'm going to use this graph here to help me, use it as a guide when I go to graph this polar equation on the polar grid. All right. So again, here's the polar grid. Say polar. So a vertical axis, which really has no meaning, is just going to break up things into quadrants. Horizontal axis, also the polar axis, right? And I'm noticing here I need to have values of r of 3 and 8 and 13 show up. So that's values on the polar axis. So here's 1, there's 3, 8, and r equals 8, and then 13. And I'll draw these circles in. Because remember, in the polar grid, we're traveling around in circles centered at the origin. So here's a circle of radius 1, right, and a circle of radius 3. And hopefully, I mean, they're not perfect circles. I apologize, right? Circle of radius 8. Okay, and then a circle of radius 13. Sorry, I kind of got squeezed up here at the top of the page. All right. And then there's other circles you can imagine, right? The whole grid. Now, for different parts of this graph, I'm going to graph the equation r equals 5 sine theta plus 8. And hopefully we see one of these dimpled limacons, right? Something like this, but like a circle with a little dimple in it. All right, so for this part of the graph, that corresponds to being in the first quadrant, right? From theta equals 0 to theta equals pi over 2. The value of r goes from 8 to 13. So I'm starting on a circle of radius 8 at theta equals 0, and I'm ending on the circle of radius 13 when theta equals pi over 2. So and then I travel there in a curvy fashion. Right, in a curvy fashion. So it starts increases pretty rapidly. So it goes maybe out like this, and then slows down its increase. So maybe like this, and then coming up here. Right? So maybe something like that. Right? Just don't connect things with straight lines too often in polar coordinates. Right? You're traveling around in circles, not on rectangles. Okay, now I'm at this point. Then from pi over 2 to pi, right, theta equals pi over 2 to pi, that means I'm in this second quadrant. Again, the values of r are positive, so the graph is still going to be in the second quadrant. And if the values of r were negative, I'd be drawing my graph in the fourth quadrant, the opposing quadrant. And I'm going from r equals 13 to r equals 8. So I'm starting up here at the beginning at theta equals pi over 2. And then when theta equals pi, I'm on the circle with a radius of 8. I need to end there. And the value of the radius is slowly decreasing at first, and then more rapidly decreasing, and then slowly again. So maybe something like this. So slowly at first, then more rapidly decreasing, and then slowly again. So maybe something like that. Again, it should they should be symmetrical. This is pretty crappy on my end. Okay, so these should be more symmetrical. This should be very symmetrical. I'm sorry about the lack of symmetry here. I'll do it on a calculator in a second to give you a prettier picture. All right, then for this next piece of this graph up here, from pi to 3 pi over 2, that's going to be in where I'm in quadrant 3. Again, the values of r, the y-coordinates are positive, so I'm going to be graphing in quadrant 3 and not in the opposing quadrant, right? If you have negative r values, you're graphing in the opposing quadrant. And I'm going from r equals 8 to r equals 3. Right? So I'm starting here at theta equals pi on a circle of radius 8. And then when theta equals 3 pi over 2, I'm ending on this circle with a radius of 3. And it's, slowly decreasing from 8 to 3. So again, maybe just continuing this curve and then coming down into here. All right. And then finishing it off, going from 3 pi over 2 to 2 pi. This piece of the graph up here corresponds to being down here in quadrant 4. Going from a radius of 3 to a radius of 8, so from this point to this point, and slowly increasing. So you see it's like a circle, but there's this little dimple here. I probably should have made that a little curvier. All right, little dimple. All right, a dimple limacon. And the larger this ratio gets, the constant to the coefficient, the larger that ratio gets, the more circular the graph looks. I probably showed you that in the first video on these limacons. All right, now let's take a look at a better picture. I'm going to go to that free online graphing calculator called Desmos, right? Desmos.com. And let me graph this. We have r equals 5 times the sine of theta. You can just type the word theta. And then plus 8. Yeah, you see that it was more dimpled than I had, and a little dimple at the bottom here. But you see this graph looks pretty similar to what I had drawn. It's a lot prettier and a lot more symmetrical, a lot smoother, and the dimple is more obvious, right, than what I drew. But this is called, again, a dimpled limacon, right, like a snail shell. Imagine a shell on the back of a snail. That's where, whoever named these things, some French mathematician, right, named it after a snail shell. Okay, and then back on the problem, I'm going to enter which one does ours look like. Not that, not that. Now now you gotta be careful. Remember, our points need to be on the proper places. This point at the bottom of the dimple should have been on a circle with a radius of 3, which this is. This point at the top of the limacon needs to be on a circle with a radius of 13, which it looks like it's higher than a radius of 12, so this looks like our dimple limacon. Yeah, this one, see, this is on a radius of 13, but this point on the top is on a circle with a radius less than 12. But our limacon, the point on top was on a circle with a radius of 13. It was 13 units away. This is too small. So you gotta really pay attention to how far points away are from the pole. All right, great. So again, hopefully watching me do this another time. I know in the first video I had a limacon with an inner loop, right, where that ratio of a to b, the constant to the coefficient, was less than 1, had a magnitude less than 1. You get those limacons with an inner loop or a double looped limacon. Here the ratio of the constant to the coefficient a over b was greater than 1, and you get one of these dimpled limacons. Hopefully watching me do this a couple times and looking at the graphs in Desmos, and really you could just go to Desmos if you wanted and punch in this equation here and see the graph for yourself. Just make sure it's in radian mode. You could do that and then just make sure you select the right one based on the way the graph's looking on Desmos. Reading your more instruction when you need to, reading the answer explanations when they come up. I'm hoping all this stuff helps you, when you go about doing this on your own. And thank you very much for watching.